Hey kiddos, here's the extra example problem that I promised you in class today. So this one involves an object going up and coming back down again. So a football game customarily begins with a coin toss to determine who kicks off. The referee tosses the coin up in the air with initial speed of 5 meters per second. The referee is very enthusiastic. In the absence of air resistance, how high does the coin go above its point of release? Okay, so what we've got here is I'm going to start writing down our knowns. Okay, so we've got initial speed is 5 meters per second. In the absence of air resistance, how high does the coin go? So we're talking about idealized free fall. So the acceleration is due to gravity and it's 9.81 meters per second squared. And it's asking how high does the coin go? Now, if you've ever watched something go up and come down, right, its motion is such that when the object reaches its highest point in its motion, it stops for an instant before it turns around and comes back down. So at the highest point, the coin's velocity is 0. So we're going to call V final at its highest height as 0 meters per second. And we want to know how high. So we're looking for vertical displacement. Okay, now I have to draw a picture. Really high quality doodles going on here. Okay, we've got that coin and it's going up into the air. And it will come back down. It probably goes straight up and straight down, but I like to kind of draw this parabolic path just to differentiate the part that's going up from the part that's coming down. And we've got the initial velocity is upwards. Okay, now here's the deal. The ground is obviously there. We have no idea how tall the ground is or how tall the referee is. Okay, sorry, I was interrupted there for a second. So we've got a ball that is going straight vertically up. We don't know how tall the referee is or the distance between the release point of the coin and the ground. And so here we can't have the ground as our reference point for height. And so what we need to do is remember we need to set where 0 height is. We don't know where the ground is, and so the ground can't be our 0 height. So we're just going to say height is equal to 0 at the point of release. All right, and then we also need to set what direction is positive. Our coin is going to be going up and going down. The coin will be caught at the same height as the release point. It'll never go below that. And so let's just say up is positive. All right. And we know that when the coin reaches its highest height, that is where the velocity is 0. And we're going to call that velocity final for the question that we're being asked. It doesn't mean that the coin that's the end of the coin's motion. It's just the other velocity that we're considering in this. Okay, and so what we're solving for is the vertical displacement between the release point and the highest height. Okay, so we're going to use our master motion equation. So remember, d equals 1/2 at squared plus v initial t plus d initial. Okay, and we're going to translate that into vertical notation. So vertical displacement equals 1/2 gt squared plus the initial t plus y initial. Now here, the initial height is how far the object we're considering, how far it is from where we've defined zero, our zero position to be. And our coin is starting at where we've defined zero position. So this is going away. The difference here now is that we do have some initial velocity for this. And we've got acceleration that is pulling down. Right? The initial velocity is upward. Okay, so based on our definition of the direction, our initial velocity will remain positive, but gravity is pulling down. Right, so we need to make gravity negative in order for us to get a correct answer using this as our problem-solving tool. Okay, so let's apply this equation. Y equals 1/2 negative 9.8. And hey, just kidding, we don't have any information about time. Okay, so let's try this again. We don't have any information about time, and so we do need to choose a different equation. We're looking for displacement, initial and final velocity, and acceleration. We don't have time, and so we do have one equation that we derived that allows us to solve for aspects of an object's motion in which we don't have time as a piece of information available. Okay, so here it is. Instead of writing 2AD, like the motion equation you've got in your notes, we'll write it as 2, right? The acceleration is g, and the displacement we're looking for, we're specifically calling it y. Okay, so this is an instant where we're specifying our notation in familiar motion equations. Okay, so final velocity at the height that we're considering is 0 equals 5 squared plus 2 times our acceleration due to gravity. It's important that it's entered as negative, and we're solving for this vertical displacement. Okay, so if we do some algebra, we'll bring this 5 squared over, and it'll become negative 25 equals negative 19.62 times y. And when we solve for y, we get 25 divided by 19.62. 1.27 meters. Okay, in my calculator I got 1.274020999, but we're rounding to 3 sig figs because that's what we have available. Okay, so that coin went up to a height of 1 meter 27 centimeters above its point of release. Okay, now we're asking about what was the total time the coin is in the air before returning to its point of release. Now there are a couple ways that we can solve for this. We know that an object, when it's thrown up and comes back down, is exhibiting parabolic motion, right? Its motion can be described using a quadratic equation, which is a parabola. We know parabolas are symmetrical. Okay, so the total time the coin is in the air before returning to its release point is the total time it takes to go up to its highest point and back down to that same height because parabolas are symmetrical, this final, v final, that's the final velocity will have a value. Okay. We'll have a value that's equal and opposite to v initial. Right, so here we can say v initial equals 5 meters per second. That was its launch speed. If the coin returns back to that same height, it will have a final velocity that's equal and opposite to that. So it would be negative 5 meters per second. The same speed, but going in the opposite direction. Okay, so for this, I can have my final velocity be the velocity at the point that the coin has returned to its release point. We're not saying that the referee is catching the coin, and so the final velocity is 0. We always want a non-zero value. Like if we're solving a problem and an object might be caught or it might land on the ground, we don't want that velocity to be 0 because the object is caught or because it will land on the ground. We're always interested in how fast is the object going the nanosecond before the ground stops it or before the person catches it. And so we're going to have the final velocity as 5 meters per second. Okay. The acceleration is due to gravity, which is negative 9.81 meters per second squared. And we're looking for time. Okay, what is the displacement? Okay, that's one more question that I can ask here. If we were to use, right, the master motion equation to solve for time, like we could solve that quadratic equation. You've probably in your calculator, you've got a tool that allows you to solve quadratic equations for time. We totally could do that if you knew the value of the displacement. Okay, remember, displacement is the total, the value of the distance in a straight line between where an object starts and where it finishes. So if we did use that master motion equation, the displacement would be 0 because the coin started out the same point where it finishes. Okay, so we could use that. There's an easier tool. Instead of solving a quadratic, physicists aren't lazy, but they use the right tool for the job. I would use, for this, v final equals acceleration times time plus v initial, where the acceleration is due to gravity. Okay, so I would do negative 5 equals 9.81 t minus, plus the initial is a positive 5. Okay, when we solve this, we subtract 5 from both sides and we get negative 10 equals 9.81 times time. And we solve for a time. Oh, and this is negative. That's important. If you ever get an answer for a negative time, that means negative times mean that somehow you've gone back in time, and I haven't invented a time machine yet. So you should be concerned if you get negative times. So you got a time that's about 1 second. Okay. Let's get the exact value here. Okay, we've got 1.02 seconds, written with 3 sig figs. All right, there you go. Let me know if you have any questions about this problem.